Right, and we're recording. Today's the 1st of September. We've got a new month and a new topic. Well, sort of. We're going to start projectile motion. Hey, you guys see a good projectile question there. Cannon blast and cannonball at some angle. The quiz on this is I'm going to combine with the linear motion and just make it a kinematic quiz. I'm working on that. So partially made those quizzes, but I'll get that to you guys by the end of next week. Okay. Before I get rolling too far on this, I want to flash up here for you guys for the video, miniaturized versions of all the posters I've been hanging up on my wall so far this year. You guys have seen some new ones popping. So this is the first one you guys saw, trigonometry. Now I should say that these two triangles are similar triangles. So all 6 of these formulas do apply to both, just in case you're wondering. Let's both of those. This one on the right is really a rotated version of this one on the left. And if you notice real close, the one on the right is actually the solution to one of your, the last quiz question. Just remember, if there's a weight pulling straight down and sitting on an incline, you break those into components. That's exactly what that shows. Okay. You guys have seen balls dropped off cliffs. There's graphs. There's a table of values that goes with that. Okay. Then we started throwing balls, throwing them up, throwing them down. I do have a little poster for throwing the ball upward. Okay, there you go. There's an example table of numbers that could possibly match with those. Okay. Oh, hey, you guys remember this? Homework options? Now I'm going to pick up linear motion homework from you guys in a couple of days, right? But this deal is still on the table. So if you wanted to start crafting a YouTube channel and send me a link for that instead, for example, or do one of these things, and yeah, still holds. 3 kinematic formulas. Good thing about projectile motion is that I don't actually have any new formulas for you guys. We're going to take everything you guys have learned so far, these 3 amigos combined with some trigonometry, and put it all together. Now look at this one right here. So here's a new poster that popped up in the room this week. Doesn't that look a lot like the starter question? Sure does. Okay. And this is how we're going to make sense of projectiles. We're going to have to analyze the motion strictly horizontally and strictly vertically, and then we'll go back and put it together all at the end. Okay. So see, when a cannon is blasting a cannonball at some angle from the horizontal in this case, okay, that cannonball leaving the nozzle is partly moving across the field and also partly moving up. Okay. How much? Oh, well, that's just cosine and sine components. You guys see that? Okay. So whatever the blast speed is, multiply by cosine of that angle to get how fast across the field is going. Multiply by sine angle to figure out how fast up it's going. That makes sense? Okay. Now here's the thing about that too. Why are we splitting this up into different parts? Because gravity will be affecting this cannonball when it's in motion, but gravity only pulls which way? Down, straight down, vertically, right? Okay. Back on the poster in class, I did actually pencil in also the actual motion of the ball. You guys see like a kind of a gray line on the poster hanging in class? You guys see it there? Right. Which it's going to go to a projectile, a parabola shape, because it's going to be a projectile. Right? But tying these ideas together, you guys see that in the x direction, I just call it v sub x. So that subscript x in this context just means in the x direction, just going straight to the right. But look at the vertical direction. It doesn't say v sub y, which would be consistent with this. It says v naught y, right? Because that's an initial condition. Because like 1 second later, right, gravity will have been pulling it down for a second. It's going to be going a little bit slower, isn't it? Okay, that makes sense. They get ahead a few steps. Right. Now, eventually, this is going to go into of course, a parabola shape, and eventually start coming back down. Okay. A setup we're going to look at later is by the end of class, I'll be sitting a cannon on top of a cliff and just aiming straight horizontal. But if you think about it, this is actually, you can also almost sort of put these together, right? Like if this one's blasting a cannonball, it goes into projectile shape. Isn't this like after it's hit the peak and comes back down, it would actually also be represented by this poster also? Right? So this could almost lead to this. This is like the second half of this problem, sort of, right? It'll eventually lead there. And here we can see what's going on strictly horizontally versus what's going on vertically. Right? You see that? See if here's the actual path of the ball, right? Follows a nice parabola. Here's the vertex of the parabola right at the cannon nozzle. Okay? But if you're up here on a blimp, watching the whole thing happen below, aren't you just pretty much picking up the horizontal motion? And hey, look, every single second, if you take a snapshot, see how the ball's like equally spaced horizontally, right? Just going straight across. That's because gravity is not pulling vertically. Guys, if gravity only pulls vertically, right? Gravity doesn't pull horizontally. Right? If we've been ignoring air drag, and that's going to continue, then are there any horizontal forces at all? I mean, once it's left the cannon nozzle, are there any horizontal forces? No. So it's just going to keep doing what it's doing. Right? X equals VT can tell you how far it went, if you know the blast speed. Right? Now, vertically, it's a bit trickier because gravity is pulling, so you have to consider that it's accelerating. If you want to know something like how far is it falling, that's your 1/2 gt squared. Right? Isn't that? Okay, so really is all we're doing is taking stuff that you guys already know in class. We're just taking it to 2 dimensions. Okay. Let's flip my screen because I want to show you guys an animation of that also. Present screen 2. Okay. Gotta rewind this film a little bit. All right, here we go. Okay. So cannon, boom, blast that cannonball. There's some total velocity. Like if you have a radar gun right at that ball at that moment, it's going to read some speed, which is represented by that orange vector. Okay? But the way we're going to analyze all the motion is we have to do this. Split that into components. Okay? There's going to be a horizontal component and a vertical component. Now, the way I'll do this, and the way I'll draw this, the way I did draw it, drew it on the poster right there, is I actually made a right triangle. You guys see if you take that green vector, I should say component vector, and you slide it to the right, pop right in place right here, make like a little right triangle. Is that's how I draw it. Some textbooks do exactly what you're seeing on the screen there. Right? But important thing, we got component vectors. Now let's watch the motion of this ball as it's flying through the air. Sorry, my computer's a little choppy. Let me go back. Okay. Yeah, take a look at that motion. Right? You see that orange total speed, and then you see the red and green components. Let's focus on that red horizontal component. Look at that red horizontal component. Right? That represents the horizontal velocity of the ball. Is that red vector changing? No. Right? And why would it? I mean, if we're ignoring air drag and gravity's not pulling it horizontal, yeah, it's just going constant speed to the right, just horizontally. Okay. What about that green vector? That green vector is definitely being pulled down by gravity. Who can tell me at what rate is that green vector changing? Yeah, you guys hear Joshua saying 10 meters per second per passing second. That's called 10 meters per second squared. Right? So it changes by 10 meters per second per passing second towards the ground. Okay? All right, I think you guys are ready to get rolling on this question. So back over to projection. Okay. You guys see that this cannonball has blast speed at an angle above the horizontal. Hey, that angle might look familiar. You guys have seen this angle before in this class. I want to think ahead of these steps. But here's my questions to start us out. What are the horizontal and vertical components of that blast velocity? Oh, that's exactly where I'm leading you guys, right? Right. That'll allow us to start this problem. And then we're going to, whatever questions come after that, we're going to analyze from either strictly horizontal or strictly vertical motion. And at the very end, we can put it all back together. So question, what is the maximum height that the cannonball goes up to? Right? You guys imagine if this is going to go into like a parabola shape, probably has some peak height, right? And that's strictly vertical information, isn't it? Right? How high does the ball go to? That's vertical, right? Probably something to do with gravity. I mean, if there was no gravity, it would just fly into space forever. Infinite height, but it's going to pull back down. And next question, last question I got here. What is the range? That's to say, how far does it go horizontally before it lands on the ground? Maybe this is like a very long, flat plane, and we were trying to hit a target over here. Right? That might be a good number to know, right? How far does the cannonball go? Maybe you're trying to adjust the angle to hit a specific target, but we'll do the easier version. Let's say we know the angle, why not figure out how far. All right, so let's start with this first question because we need to answer this first question before we can answer anything else. Right? What are the components of this thing? So let me pull this to the side. I'm just going to redraw that picture while you guys are drawing this in your notes. Got cannon. It's angled up at a 53-degree angle from the horizontal. That's a pretty steep angle. Pretty good angle going on right there, right? Okay. So it's also blasting at exactly 100 meters per second. By the way, that's over 200 miles an hour, in case you wanted a comparison. Got a flat plane going on here. Okay. And maybe in green, I'll draw the motion of the ball. The actual cannonball is going to probably be something kind of like this. Whee! Land way over there. Ooh, actually, that's not bad. Right. that look like a parabola, upside down parabola? You said? Okay. All right, so let's do components. Now, on my poster, I'm using kind of a bluish color for horizontal. So it could be like this. Call this V sub x. Oh, don't forget that this is, of course, a 53-degree angle. Okay. And then the upward part, well, on my posters, I've got it sort of like an orange color, so got a red pen here. Very pretty close. I'll call this, now, I call this blue one V sub x. Do I want to call this not V sub y? I'll call it V not y, because it's only an initial condition, right? Remember, as soon as it leaves the cannon nozzle, it goes into free fall, gravity starts pulling down, this number will immediately start changing, right? Now your formula for this, oh, who can tell me? What times what? How fast across? What times what? Isn't it 100 meters per second multiplied by sine or cosine of 53? Cosine, good call. Okay. And then vice versa for the V naught y, this would be 100 meters per second times sine of 53 degrees. Let's get some numbers. 100 cosine 53 is, hey, exactly 60 meters per second. That's going to the right. Huh. Okay. And then, what's the red one going to be? 80. Yeah, it is 80. Because scroll up, scroll over, pop in a sine with a cosine. Yep, 80, exactly. 80 meters per second. I bet so many guys knew what those numbers were going to be, maybe even without a calculator. Because I bet some of you guys were looking at that 53-degree angle thinking, ooh, that is going to turn out to be a what triangle?
3, 4, 5 triangle.
That is a 3, 4, 5 triangle. You guys see that? The ratios of legs are 60, 80, 100. That reduces to 3, 4, 5. Right? All right, yeah, good catch. All right, so we answered the first question, which was this right here. What are the horizontal and vertical components of that blast velocity? We got them. 60 to the right, 80 up, for a total of 100 at that 53-degree angle. Okay. Next question. What is the maximum height that cannonball goes up to? Okay. Now, maximum height. Do I care about the 60 meters per second across or the 80 meters per second straight up? You guys say.
60 meters per second.
Yeah, I definitely care about, guys, if I want this maximum height, that definitely has something to do with how fast it's going strictly upward, doesn't it? Okay. Yeah, so it's definitely that. Yeah, good call. So I'm going to label this, well, I guess I'm going from the last point. I don't know. Something like that. But H max. H max. Huh. Wonder what that height is. Right. You guys can solve this already based on your linear information. I mean, wouldn't this be the same answer as if you were to take a ball and just throw it straight up at 80 meters per second? Wouldn't that be the exact same scenario? It would go up to the same height, wouldn't it? Right? Okay. Remember, now that we've broke this into vectors, we're going to totally ignore the horizontal stuff because that doesn't matter. All we care about is the vertical part. Okay? In fact, if you guys like, we could do a whole tax DV table with this, couldn't we? Let's try that. Can I zoom out anymore? Okay, that's as much as I can zoom out. Okay. All right, so make a little checklist. All right, that's what that looks like. Now, acceleration is g, which is 10 meters per second squared toward the ground. Okay. We're trying to figure out h max. This is like our unknown value. Okay. This is really, these are really all in the y direction, aren't they? Okay. And maybe I shouldn't really say x, maybe I should say y. Okay. Like T-A-Y, B-not, yeah, right? So this way, I'm going to try to distinguish that. Anytime you see x horizontal, y is vertical. It's the same idea, right? Hey, what number goes right here? How fast is it going strictly upward initially?
80 meters per second.
80 meters per second. You guys are on. Okay. You guys have a framework with some check boxes. Just figure out what's what. Okay. If you can figure out what this number is, then you're pretty much gold. What number should go right here?
60 meters per second.
Okay.
Oh, no.
It's in the y direction. Try you guys on along with it. Oh, yeah. Perfect. 0. Yeah, you guys catch that? Yeah, so Carson's saying 0 meters per second. Because, why 0?
Because then it's landed.
Yeah. Yeah, when it's at the top, because we're trying to figure out this H max, right? You know what I should have done, but I'll do this right now, is identify the points that we're going from and to. Here's the initial point. It just left the cannon. Here's the final point that would allow us to solve for H max, right? Are we going from point A to point B, initial to final? Right? We've been doing that for over a week now. Whenever solving these kinematic problems, we're always picking point A, point B, initial, final. Okay? And right at this top star, the cannonball is, well, approaching it, it's going up, 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 and leaving it, it's coming down, 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 down. So, remember at the very peak, the ball has 0 velocity vertically, right? Well, if you throw a ball straight up, it just playing at 0 velocity, but it's going on some angle. Right? All its velocity up here is horizontal at that point, but so 0 vertical, right? Is that? Right. Great. That's 3 kinematic values, isn't it? Right? I mean, once you've identified those, now, if you wanted to be really formulaic and routine about it, you've got some formulas. So, which equation looks like it's going to let us solve for the height based on the information that we know? First, second, or third? You guys say the third? I like the third one too, right? Because notice the third one doesn't mention anything about time, and well, that's not being asked for, and we don't really know it either. Yeah, let's do the third one. That's the fastest way to solve this. Not the only way, but fast way. Good problem. Final velocity in the y direction squared equals initial velocity in the y direction squared plus, well, 2ay, right? Now, you know what? I got to be careful with my numbers. Tell you what, see these 3 numbers? One of them is not exactly correct. I've got a little detail that's wrong. What's a little bit wrong? Which way is this cannonball being blasted? Up. Which way is gravity pulling?
Down.
Down. Somebody's got to be negative. Throw the negative there. Just got to take a number, right? All right. Plug in some stuff. I know that at the top it goes to 0 meters per second. It was being blasted 80 meters per second strictly upwards. And that's all I care about. Just focus on the up direction. Because gravity is pulling straight down. And then this would represent H max for that particular scenario. Right? So if you can get to that point, then you have pretty well mastered kinematic motion, because we are done with the physics and we're going to go on to algebra. Right? Just to finish this out, it's just a bunch of algebra steps, right? Is that? Right? Right. So we're done so far. You said we know the blast speed and the angle, so you split that into components. You identify if you want to know how far up does it go. That's a vertical question. You pull together all your vertical information, and there's just enough information lying around where you can solve for it, and that's what we're about to do. So 0 equals 100 minus 20. That would look like that, right? Okay. Put that over. So 20 H max is equal to 6,400. Then a bunch of weird units. Okay. Okay, now all the seconds cancel. One of the meters cancels. Divide both sides by 20. That's 6,400 on 20. So the number is 320. And the only unit left on the board once you do all the unit canceling ends up being meters, which definitely makes sense because meters could measure a height. Yeah. Exactly what we're looking for. Okay. That's how high that cannonball goes. Ooh. That's a pretty good distance up. That's like 3 football fields up, isn't it? Yeah. Go label that. So back on the original, well, do that there for a few seconds. Okay. While you're finishing copying that, go recap what. Okay, so identified 3 vertical motion variables. These are all strictly vertical, right? Okay. You guys chose the correct equation to get us the answer the fastest. We're looking for a displacement in this case, displacement between this point and this point. Okay. Plug in the values. This is how fast it was going up. This is the rate that's being pulled down. Right. It ends up at this speed vertically. Okay. Chug, chug, chug. 320 meters. This is 320 meters. guys good? Okay. Wait. Oh, there was still another question though. So we broke the original velocity into components. Bing, done. Maximum height. Bing, done. What's the range? How far does that cannonball go downfield before it hits the ground again? Because this is like just a very, very long plane. Okay. What's this distance from here to here? Huh. So this distance, right? Call that x. What is x? What is x? Okay. How many guys are looking at that 60 meters per second that's going to the right saying, hey, if it's going at that speed, and that's going to be constant all the way across, isn't that true? You guys remember from that animation? Like, it's not speeding up or slowing down to the right. Right? That if only you knew the time that was in there, called the hang time, if you knew the hang time, couldn't you just take this number, multiply by the hang time, distance equals speed times time? Boom, 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 done. Yeah. Okay, so really, we need to answer another question first. Before we can get this, we need to know something about time. How much time is it in the air? And you know what? If you look back at the vertical information we just did, it's just begging to be solved, isn't it? Could you just solve time from this right here? Okay. Now, before we do that, there's a caveat. Okay. Solving for range, isn't that from like this star to this star? That's the range. Okay. But this setup that we just did is not from there to there. The setup we just did is from here to here, right? So if you solve for time using exactly these numbers, doesn't that represent half of the hang time? You guys get? Because to go from this star to this star, which is established as soon as you call VFY 0, you're saying it's not moving up or down right at the top. Okay. If you solve for the time to get to the top, that's only half of the total time, right? So we could do this, solve that, and then just double the answer. You guys get it? That's it. So I'm still going to play off these numbers. The fresh page here. Okay. In fact, I bet you guys could figure out that a good equation to use might be, you guys got some options. I'll do this one. X equals v naught t plus half at squared. Yeah. Okay. You also could have done the second equation. That would have been fine. Okay. But this is represented by h. Max, it's really y. Maybe we should set y. Okay. V naught is, well, V naught y. This is half the hang time is what, I changed my mind. Guys, if I try to solve time using this, I'm going to run into what situation? Starts with a Q. Quadratic? Okay, we could do that, but let's start from scratch. There's a much faster way to do it. Okay. Let's do this one. VF equals V naught plus AT. Something like that. All right. When I say plus AT, well, gravity's pulling down, so maybe we could say like minus GT. That'd probably be a good modification of that one. Right? So, all right. Because we know this number goes to 0 at the very top, 0 meters per second. Now remember, that's strictly vertical. That's okay. It started out at 80 meters per second. Again, strictly vertical. That's okay. And then being pulled down at a rate of 10 meters per second squared for some time. Okay. But keep in mind that this time actually represents half the hang time. Okay. So full subscript has said half the hang time. Just the time to get to the top. Any questions so far? Questions? All right. So add this over. I'll get 10 t half hang time is equal to 80. Okay. Those numbers have units. Okay. Divide both sides by 10 meters per second squared. The meters cancel. One of the seconds cancels. 1 of the seconds flips back up top. And half the hang time comes out to be 8 seconds. Right? Guys got that? And this will be a common pattern you'll see with all these projectile problems, is that the amount of time that a projectile is in the air is constrained by its vertical information because it has something to do with the gravity pull. Right? Let's go back to the picture and put this all together. Right? So you guys know 8 seconds, that's to get from the cannon to the very top, right? Okay, so from there, because that's what we set up, because we let BFY go to 0, which would be the star. Okay? So could you guys imagine if you turned up gravity, like made gravity stronger, this thing would probably go boom, and be in the air for a very short time and land right about here, like that? To make these stars kind of same elevation, I guess. Okay. Yeah, so change gravity is going to change the time, so that's a vertical. Got that from vertical. All right, so if we want the total hang time, so full hang time, isn't it just this times 2, right? So 16 seconds. Is that okay? All right, you guys good? All right. So this cannonball took 8 seconds to reach the top. Therefore, it would, by symmetry, another 8 seconds to fall back down, and the full hang time is 16 seconds. It was in the air for 16 seconds. Okay? Okay. All right. What do we? We're about to get the final answer, because now we got to go to horizontal information. Right? I want to know x. What is x going to be? Popped up right here. Okay. And because horizontally there's no acceleration, isn't it just always going to be some version of this formula, x equals vt? As long as you're not accelerating, just this, isn't it? Okay. Now this is, of course, v sub x. This subscript refers to direction. Okay. So how far does the cannonball go? Well, it was going at 60 meters per second strictly to the right. That came from here. And it did that for 16 seconds, didn't it? Okay. Remember? 8 seconds up, 8 down. So it was traveling to the right for a total of 16 seconds. What does that come out to be? It was 60 times 16. Woo! The seconds cancel, get meters. 960 meters. That's almost a kilometer. That is a good blast distance right there. But I can believe that because this is a really fast blast speed. I mean, 100 meters per second. That's like over 200 miles an hour. So, okay. Okay. You guys good? Okay. So I took you guys through all these questions. Right? Here's a recap. Right? If you know the blast speed, the angle, you can split that into components, figure out how fast strictly up, how fast strictly to the side. Right? You can use strictly the vertical information to figure out how high does the cannonball go. And you can also use the vertical information to figure out how much time it's in the air for. And once you know the time, then you can say, well, how fast it's going across, multiply that by the time, I'll get the range, let's say how far it goes horizontally. Right? You guys good? All right, so that's the first time you guys have seen a projectile, but let's see, get in one more example. All right, got almost 20 minutes. Great. So, oops, that's not one. Here's what I want. All right, you guys have a new page with boxes on it. I had you guys pick this up from the side of your desk within the last couple of days. Right. So let's look at this first scenario. It says a cannon fires a cannonball horizontally at some given horizontal velocity off the edge of a cliff. Edge of a cliff. You know what we're doing? We're going from to the last situation we did. Whoops, let me zoom out for you guys in class. Okay. The last situation we did started off looking like that. And the problem we're doing right now, just from that first sentence, you can already tell it's going to look exactly like this, isn't it? Right? It's going to look like that. Okay. So there's you guys' image. Of course, I'll draw that too. Get this side. Whoops. All right, zoom back in so you guys can read this. Okay. Cannonball fires a cannonball horizontally from the edge of the cliff. The cannonball lands at some given horizontal displacement away from the base of the cliff. So we fired it off. We saw where the cannonball landed. Went out and measured. How far did it go? So that's probably easily measurable. Okay. Can you find, whole list of questions here. Okay. How much time did it take for the cannonball to reach the ground? Can you figure out what the height of the cliff is? Can you figure out, no, the third question says vertical component of velocity right as the cannonball is about to strike the ground. That's really just a step to answer this very last question. What's the total speed that the cannonball hits the ground? Okay. Do you guys agree that however fast that cannonball is firing, if it's being pulled down towards the ground, it's going to speed up a little bit before it hits the ground, right, overall? Okay. But the only way to figure out exactly the total speed is to do all these components that we've been doing since forever in this class. So, here's that. You zoom out. Okay. Okay. We got to draw that cliff. Get a recreation. Like this. Okay. Perch cannon up here. Okay. Now this one's firing straight horizontal. So I've got to aim straight horizontal. Let's have, I'm going to use blue for this. Okay. Now the blast speed and the horizontal speed in this case are the same thing, which is, yeah. Okay. I'll call this, well, I could call it V blast, but it's really the same thing as V sub X because the cannon is aimed straight horizontal in this case. Okay. Okay. And then the actual path that goes is going to be something kind of like this. You see a parabola? A parabola path with the vertex of the parabola right at the cannon, where the cannon is. A little boulder. Okay. Maybe we do a few shots and it just keeps hitting the same spot. Land right there. Okay. Oh, no, what information did I give you? Oh, I told you how far from the base it is. Told you this number. I'm going to make up my own numbers. Let me call this 500 meters. I say it landed 500 meters away. And for the blast speed, again, I'm just going to make up a number. Let's say it's 100 meters per second. Same as the last cannon, right? That's how fast it's firing. That's how far it goes, right? And you also know gravity. 10 meters per second squared straight down. I know on your paper it says 9.8, so in my notes I'll use 10. Close enough. Okay. That's it. That's all you know. Okay. Okay. Now, while you're thinking about that, okay, I bet you guys can figure this out. Okay. But I want to make a point about why I set this paper up the way I did. Because so we got some boxes, got these convenient tables. Okay. Now, notice I split this into actually two separate tables. Okay. One table only has 3 columns in it, right? Now the 3-column table right there that you're looking at, does that refer to horizontal or vertical information? What do you guys say? See, versus the 5-column table. Well, which one has acceleration? The 5-column, right? And acceleration, which way is it accelerating? Down. So the 5-column must refer to the vertical stuff, right? And the 3-column refers to horizontal, right? Because horizontally, isn't it just x equals vt? Right? There's no acceleration, right? You guys know that? Right? I was making this deal too back when we were doing linear motion of if you know a certain number of things, then at some point everything becomes determinable. Right? So on the 5-column table, how much information do you need to solve anything? 3. You need three values, right? And it looks like I can only identify 2 here. I know that gravity's pulling down at this rate, and I also know that, see if you aim something straight horizontal, then right as this cannonball is leaving this cannon, isn't it neither moving up nor down? So it could say this, it could say v naught y is 0, but that's only 2 pieces of information. So in isolation, this is not yet solvable, right? But the fact that I know exactly how far the cannonball went, it's eventually solvable, right? Because, hey, distance equals speed times time. Let's think about a roadmap, what we're about to do. Could you guys figure out how much time it's in the air just based on this? Do x equals vt? You could. And then if you know the amount of time that it's been in the air for to get from here to here, from point A to point B, beginning to end, okay, then whether you analyze it horizontally or vertically, doesn't this take the same time either way? Right? Now, of all the variables listed on either of those tables, they are all vector values except for time. Time is a scalar. You guys remember that? Right? Now, here's one reason that that's important. because vector values are only applicable in their particular direction, right? So all these numbers that you guys see already printed are either strictly vertical or strictly horizontal, right? But that's not true for time, right? Time can transfer either way, right? So once you solve this time, however much time it takes to go across the field, doesn't that exactly apply to the vertical stuff too? It also took exactly that time to fall down the cliff, right? So you guys can transfer that. In fact, what you might want to do on your paper is do something else, like circle this and go, like just draw an arrow, it's going to connect. These boxes have to be the same number of seconds, okay? All right, you guys got that? All right, so let's, for the video too, for the visual, I'll go and do that. Whatever that number is, we're going to transfer it over there. Okay. Do x equals vt, solve that, transfer the number, then we'll have 3 variables, then we can solve, get whatever we want. That's the roadmap. Okay, you guys get that? Okay. That's our roadmap. Okay, so let's definitely start with horizontal information, because I know zoom out. I know 2 pieces of horizontal information. I know how far, I know how fast, therefore we can solve time, and then we'll be on our merry way. X equals VT. Now throw a little subscript X on that V to say denote horizontal direction. I know it went 500 meters at a rate of 100 meters per second. I see you just divide both sides by 100 meters per second. The meters cancel, seconds floats back up top. I'm going to get a time of 500 over 100. That's 5 seconds. 5 seconds. Oh, all right. That's how much time it took to get from here to here. 5 seconds. Guys got that? Okay. Now we did the horizontal analysis, but of course that also applies vertically. Right? All right, you guys ready for vertical stuff? What was the next question? It was what's the height of the cliff? Okay, so that's answer number 1. Okay, number 2, what's the height of the cliff? Okay, let's do another table. Except this will be vertical. So I'll do a tax VV table, but it'll be something more like this. The G, Y, V naught Y, F Y. Isn't that a tax VV table, but just modified for vertical information? Okay. Here's how much it's accelerating vertically. Okay. Here's the vertical displacement, height of the cliff. I should label that on my picture. I should label Y. This is actually H cliff, isn't it? Height of the cliff. H cliff. Height of the cliff. Okay. This number is, what is this number according to my setup right here? When the cannonball leaves the cannon, how fast is it traveling up or down? Zero. It's not traveling up or down. It's only going to the side. So this is 0 meters per second. Okay. Now, of course, that immediately starts changing. Gravity starts pulling it down. But at the initial point, it's that. Okay. And we know what time is. Did we just do a bunch of work to figure out the time was 5 seconds? Oh, and of course, gravity is 10 meters per second squared. I'll call it down positive. That way, all my numbers are positive. Okay. We're trying to figure out what that is. We have 3 things now, don't we? Right? You guys good? Okay. So, you bring in the 3 amigos. You say, I want to figure out what the height of the cliff is. I know how much time has passed. That's got to be which equation? First, second, or third?
First.
Yep, definitely the first one. Yeah. In fact, you know what? Of the first one. See how V naught Y is 0? Doesn't that just boil down to this? Right? About that, right? Okay. So if I write the full thing out, it's Y equals V naught YT plus half GT squared. Okay. But what I was just saying is that that's just going to zero out anyway because it goes to 0. So H cliff, solving for, is equal to, okay, well that just goes away. Okay. Got 1/2 G times T squared, right? Where you guys know that square only applies to the time, right? Just the 5 that's being squared. Right. And what's that going to be? 1/2 times 10 times 5 squared. Hey, look at that. It's about 125 meters. Whoa, have we solved this before? You guys seen this before? You guys remember Paul Hewitt in the mine shaft? You drop the rock. You count to 5. Takes 5 seconds. About 125 meters deep. Hey, that's the Paul Hewitt problem, isn't it? Yeah. You guys seen that before. That answers that question. Oh, okay, so we go back to the picture, label what we know. We know that this came out to be a 125 meter tall cliff. We know time now came out to be 5 seconds. And, okay, well, that's all our new info. And we already know those two values. Okay. The next, actually, the next pair of questions get at something to do with the cannonball landing at this last spot. Now, you guys agree that that cannonball is probably coming in sort of on an angle like this, right? Okay. I'll call this V crash, like the crash velocity. It's coming in on an angle, right? But remember how we started the last question is that we were blasting the cannonball at an angle and we immediately split that into components, right? This one's going to end sort of the mirror image of that, which is that the only way to figure this out is to know what the components are and to put them together right at the end. So coming in for the landing, it's kind of going across, it's only V sub x. And it's also kind of coming down at the same time with some V final in the y direction, right? That makes sense? Right? And if I have time, then I will also take you guys over this crash angle, but I'll try to fit that in before the bell. Right. Hey, look at this Vx. Did that stay the same all the way across? It had to have. This thing was not accelerating horizontally. So I know this number already. It has to be 100 meters per second across, right? Isn't that? It was 100 meters per second across the entire way. Right? Now VFY, maybe I could take advantage of this info and just solve for this guy right here. That's basically what it should do, shouldn't it? Right? Is that? You guys like the second equation for that? Or you can do second or third. I'll pick the second one. VFY, solving for, equals V naught Y plus GT. Right? Am I clear? Right. And this number, of course, was just 0 meters per second. That goes away. Okay. So final velocity in the y direction is, I got 10 meters per second squared. Do that for 5 seconds, right? Wouldn't that be 50 meters per second? That's final velocity in the y direction. Let's say final velocity in the y direction came out to be 50 meters per second, right? And that's just your linear motion info. Okay? So this came out to be 50 meters per second, right? Who's got questions so far? That's good. That actually answered question number 3. But like I said, it's really a step up to answer this last question. I really want to know this. How fast is this cannonball crash landing? Because if blasted at 100, gravity's been pulling down, it better be speeding up. How much did it speed up? Well, we're about to figure out by doing the Pythagorean theorem. You guys see it's going to be Pythagorean? You guys see that? Let's do that. Pythagorean theorem time. So I'm going to go V crash squared is equal to, well, Vx squared plus Vy squared, so that works out like this number squared plus this number squared, right? Squared up there. Right. So can I add those together, take the square root? Okay. So square root, all this stuff. Let's see, what is square root of 100 squared plus 50 squared? Looking at V crash, once I do all the square root stuff. Those are, make that prettier. Came out to be 112 meters per second. Okay, and that is question number 4. Oh, that's the answer to question number 4. 112 meters per second. Okay. Okay, so let me take you guys through, recap of the whole problem. Okay. You know the blast speed of the cannon, straight horizontal. And because you know how far it goes, you can solve for time. That's the first thing. Came out 5 seconds. Once you know the falling time, you can start solving vertical stuff, like what was the height of the cliff. Right? You can also solve for the vertical component of velocity at the crash site. Right? And then once you have that, and you know the horizontal, because it's just the same all the way through, Pythagorean theorem to solve for crash speed. Boom, boom, done. Now, told you guys what solve this angle for you guys. Or you guys tell me, guys, this angle theta, how can you solve for it? Inverse tan? Inverse tan of maybe opposite over adjacent, right? So it'd be 100 over 50. Right. No, that's relative to the vertical. You guys see it's relative to the vertical? Right. So what is inverse tan 100 over 50? Right. That's 63 degrees from the vertical. Right. Or if you like, you could have done inverse tan of 50 over 100 from the horizontal. And try that. What is 50 over 100? Inverse tan of that. Okay. That would be 27 degrees from the horizontal. Okay. And notice, of course, those two angles add up to 90 degrees. Of course they would, right? I'm saying if you wanted this angle instead. Okay. So this angle is 63 degrees. This angle is 27 degrees. Okay. You guys good? All right. Okay. Who's got any question? Any question? You guys have a good Wednesday.